So what's the big picture on cyclic groups? Well, on the one hand, when we talk about cyclic anything, we're talking about the set of all integer powers of an element, right? So I take an element and I multiply, quote unquote, it by itself repeatedly, or I multiply its inverse by itself repeatedly, and I take all of those integer powers, they form the cyclic subgroup generated by that element. And if that cyclic subgroup turns out to be the whole group, in other words, everything in the group can be written as an integer power of one thing, then we call that one thing a generator, and we call the group cyclic, right? And the big theorem that I put down here at the bottom is kind of explains what we're talking about on daily work 10. And this theorem, I feel like we should give it like a name, call it like the fantastic theorem or something. It's the best I can do off the top of my head. But it's a fantastic theorem because it tells me so much about cyclic groups. It says if I have a finite cyclic group, so its order is n, and n is an actual number, not infinity, then it tells me that for any divisor of n that you give me, I can produce an element of order k in the group. And not only is there one of those elements, there are, Euler phi function of k, many elements of order k in my cyclic group. Right? So it gives me, first of all, a condition under which an element of order k exists, and then secondly, provides me with a way of counting how many there are. And the unspoken piece in here is, what about the non-divisors? So if L does not divide n, what can we say? So let's suppose we look at a clock again, so the usual z mod 12. How many elements of order 5 are there in z mod 12? How many different ways are there for me to take a 5-step trip around the clock by an equal number of hours forward every time? So how do I know, my assertion here is that there is no element of order 5 in z12? But why not? What's the number theory relationship between 5 and 12 that I'm trying to get to here?
Isn't it 12?
Okay, so here is a common lexical place where people get turned around in this material. So let's try and head this off at the pass, because now I've seen a couple people get this turned around. And this happened last semester when I taught the same material. So let me pick an element. So the element 5 in Z mod 12 has order. What is the order of the element 5? That's an answer to Caitlin's question. Right? The order of the element 5 is 12, because if I would need to add 5 to itself fully 12 times before I got back around to 0. On my clock. In other words, if I go 5 hours forward from 12, and then 5 hours forward from there, 5 hours forward from there, etc., 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 5 plus 5 done 12 times gets me back to 0. But no smaller power of 5 gets me back to 0. That's a different question than the one I'm trying to ask here, which is to find me an element which has order 5. So keep these two types of statements straight. 5 and 12 are relatively prime. And what does that tell me? Right, so 5 doesn't divide 12, so it's an example of one of these non-divisible examples. And so how do I answer this question? What element has order 5? This would have to be an element. So let's write what this element would have to satisfy. This would have to be an element, if we call it x. This would have to be an element which, when added to itself 5 times, would give me 0 mod 12. Right? Let's use multiplicative notation for a second so that we can use some ordinary algebra. 5 times x would have to be congruent to 0 mod 12. Okay. But how do I solve this congruence? If 5 and 12 are relatively prime, that means that if I'm multiplying 5 times x, and I'm getting something which is 0 mod 12, 0 mod 12 means it's a multiple of 12, so it's equal to 12 times m for some integer m. Right? But 5 and 12 have no factors in common. And if they have no factors in common, then that means that every factor in 5x, which is not divisible by 5, would have to be a part of this x. And every factor over here, which is not divisible by 12, would have to be a part of this m. And so the only way to solve this equation over here is that this x has to have all my 12s in it. This m would have to have all my 5s in it, basically, right? But if the x already has all the 12s in it, that must mean that this x has to be a multiple of 12, is what I'm trying to say, right? This x has got to be a multiple of 12. Since 5 and 12 are relatively prime, there's no way to make this 5x a multiple of 12, other than to make x a multiple of 12. But if x is a multiple of 12, what is x congruent to mod 12? 0. In other words, we really can divide this equation by 5 on both sides. 5 is invertible mod 12 because it's relatively prime to 12. And so whatever the inverse of 5 is, mod 12, which 5 is actually its own inverse, mod 12. 5 times 5 is equal to 1, mod 12. Multiply on both sides by that 5, I can solve this equation, x congruent to 0. But what's the order of the element 0? 0 is the identity in this group, so what is its order? Order of the identity element in any group, always 1. So the only x which satisfies 5x is congruent to 0 is x equals 0, but 0 does not have order 5. It has order 1. So what element has order 5? Nothing. Perfect. So keep those two questions straight. When you talk about, particularly when you talk about additive groups, because their elements are already numbers, it's easy to get turned around with what's an element and what's the order of that element. But two very different answers to these two very different questions, right? There is an element of order 12, namely any generator of Z12 will be an element of order 12. 5 is such an example. But no element has order 5 in Z12. And so if we generalize out that statement, what do you think is going to happen for any L which does not divide N? How many elements of that order L are there going to be in my cyclic group? None. There are no elements of order L. So, another way we could frame that is we could make this into an if and only if kind of statement. Right? K divides N if and only if there exists an element of order K in my cyclic group of order N. Right? Because then the if part of that would imply that if K doesn't divide N, there does not exist an element of order K inside of my cyclic group. So the reason that I want to spotlight this, and then when I'm trying to harp on it a lot right now, is that we had made a conjecture a couple of chapters ago about how the order of a group relates to the orders of its elements. Remember when we were looking at groups of order 4 in our gallery walk example from early in the semester? You found the orders of all of your elements, and all your orders were what? They were all divisors of 4. Yeah, they all went evenly into 4, 1, 2, and 4, right? But some of those groups were cyclic, some of those groups were not, right? And so the conjecture back then was that for any group, for any G, order of element divides order of group. That was a conjecture. And we don't know whether that's true yet. But what we do know is that not only is it true for cyclic groups, it's true on an if and only if basis for cyclic groups. Not only does every cyclic group contain elements, not only in a cyclic group will the order of all of its elements divide the order of the group, but it also goes the other way. All divisors of the order of a cyclic group have elements of that order. How many of them do they have? That's where the Euler 5 function comes in. It tells me how many elements of order K there are. So for example, how could I figure out how many generators of the group there are? What would the order of a generator of a cyclic group of order N be? N, exactly. It has to generate all the elements in the group, and so it needs to have N distinct powers, integer powers. And so phi of N tells me how many generators there are for the whole group. Phi of k, for k dividing n, tells me how many elements of order k. Those elements of order k would generate cyclic subgroups of order k. Right? So another way to think about this, since we're talking about cyclic subgroups, now is a good time to revisit subgroups for a minute, which maybe there will be an opportunity on quiz 4 to dip into your subgroup material as well. But let's go on to military time for a second. So 24-hour clock. If we could list all subgroups of Z24, what would they look like? Can somebody let's get started just by giving me an example of a subgroup of Z24? Whether it's an interesting one or an uninteresting one, I don't care. Yeah. Z12. In what sense? So I agree with you up to a point. So in what way is Z12 a subgroup of Z24? What elements would this Z12 have in it?
1 through 12, or
0 through 11. So my question for all of you is, how do we know whether this subset of Z24 is indeed a subgroup? So we don't quite have enough material in this subset to make a subgroup of Z24 because 1 doesn't have 23, its inverse, in the subset. 2 doesn't have 22, 3 doesn't have 21, and so on down the line. So this particular set of elements of Z24 is not a subgroup. But I claim that there does, in fact, exist a subgroup of Z24 which has 12 elements in it. But 1 cannot be a part of that subgroup. And the reason for that is as soon as 1 belongs to my subgroup, what else must belong to my subgroup? 23. And also 1 plus 1, 2. Everything, exactly. As soon as 1 belongs to my subgroup, then every power of 1, quote unquote, will also necessarily, by closure, belong to that subset, right? That subgroup. And therefore, since 1 is a generator of Z24, I can't have 1 without also having every single element of Z24. So that's actually an important subgroup, right? The whole group is, in fact, a subgroup. The cyclic subgroup generated by 1 would have all the elements 0 to 23. That's the biggest possible subgroup, right? Is the whole group itself. Kelly? Yeah, there we go. So there is an example of a subgroup with 12 elements in it. If I just take the even residues mod 24, 0, 2, 4, 6, 20, 22, that's got 12 elements in it. Is this a cyclic subgroup? And if so, what is an example of a generator for this set of even residues? On 24. The 2 is an example. Sure. This is the cyclic subgroup generated by 2 because it's 2 plus 2, it's 2 plus 2 plus 2, 2 plus 2 plus 2 plus 2, and so on up to 22. Right. So here's the cyclic subgroup generated by 2. It's got 12 elements in it. So what is the order of the element 2 in Z24? 12. The order of 2 is equal to 12. How many other elements of order 12 will there be in Z24? So we know there exists an element of order 12 because, of order 12, because 12 divides 24, right? So we're using, let me jump back here, we're using this first part. 12 divides 24, so there exists an element of order 12 in Z24. But how many elements of order 12 are there in Z24?
2.
2? Well, there's at least 2. Why is it 4?
Because that's the phi.
That's the Euler phi function of 12. Yeah, exactly. There's not only 1, there's not only 2, there's in fact fully 4 elements of order 12 because that's phi of 12. There's 4 elements of order 12 in this group. 2 is one of them. What's another example? What other element definitely generates the same subgroup as 2 does?
20.
20? Why 20?
Because it's the inverse of 2.
Yeah, I like where you're thinking, except 22 is actually the inverse of 2. Yeah, exactly. Yeah, no, I tricked you because I listed fewer on the right than I did on the left. Yeah, so 2 and 22 are going to generate the same cyclic subgroup, for sure. Right, so there's 2 examples of elements of order 12. The other ones are a little harder to spot. I wonder how we would find them. Let's go back to our original observation about 0, 1, 2, 3. Right? That was not a subset. Sorry, it was not a subgroup. But its doubles did form a subgroup of Z24. So 1 and 11 seem to line up with the two that are generators of the cyclic subgroup. What do you suppose the others are? So 10 isn't going to, because 10 is not relatively prime to 12. 7, and its inverse mod 12, which is 5. And so those are going to line up with which residues mod 24? 10 and 14. So we can check that 2, 10, 14, and 22. All of those are elements of Z24 that have order 12. Those are our 4 elements that have order 12 in Z24. Any one of those 4 elements, its cyclic subgroup generated by that element will be these 12. And coming back to the first response I got to this question, in what way does this resemble Z12? It's not exactly Z12, because it doesn't have 1. 1 is an example of an element of Z12, but 1 isn't a part of my subgroup. And yet, we can kind of cut all these numbers in half, and we do get something that's exactly Z12. So there is a sameness relationship here between Z12 as such and this particular cyclic subgroup. So I'm just going to kind of write in here, Z12 is the same as, until we get to chapter 6, when we can make the same a rigorous observation. But it's a cyclic subgroup having 12 elements, and therefore it is the same as Z12. So there's an example of an interesting subgroup of Z24. What's an example of another interesting, or maybe not so interesting, doesn't matter. What's another subgroup of Z24? Z4, so what you mean there is a subgroup having 4 elements in it, right? Something which is the same as Z4. What would be an example of something which would generate a 4-element subgroup? 6. 0, 6, 12, 18. Right? That would be, for example, the cyclic subgroup generated by 6. Right? That's got 4 elements in it. And so what is the order of the element 6 in Z24? 4. How many elements of order 4 would there be? What question do I have to answer there? Phi of, well, I want order 4 here. So phi of 4. I need phi of 4, elements of order 4. And how do we figure out what phi of 4 is? It'll be 2 to the 1 times 2 minus 1. Right? Because 4 is 2 squared. I think I have that right. And so the value of k here in your formula is 2. The value of p is 2. So it's p to the k minus 1 times k minus 1. Do I have that right? So 2 to the first times 2 minus 1, that's going to give me 2. Or we could manually count, right? Remember, phi of 4 is how many natural numbers less than 4 are relatively prime to 4. Well, what are the natural numbers less than 4 that are relatively prime to 4? 1 and 3. So there are 2 of them, and so phi of 4 is equal to 2. So 6 is a generator of this cyclic subgroup. What is also a generator for this cyclic subgroup? 18, yes. We know that 6 and 18 are going to generate the same cyclic subgroup because they're each other's inverses. And the inverse of an element always generates everything that the element itself does. What is it about the definition of cyclic subgroup that makes that almost obvious from the definition? Why must A and A to the power minus 1 generate the same stuff? Right, so spotting this. Generated by A. That means, colloquially, you can say A generates G. So G is equal to some power of A, right? For some integer k, G is equal to A to the k. And so the question then is, why is it also equal to some power of A inverse? What power of A inverse will it be equal to? A to the k is equal to A inverse raised to what power? Minus k, yes. That's it. And why is that okay? Why is that all right for our definition of cyclic subgroup? Because my k's, my powers that I can take of my generator include both the positive and the negative integers, and 0, of course, right? And so if k is an integer, then minus k is also an integer, right? Because the integers under addition have the inverse property. Right? They're a group, and so they have the inverse property. And so, therefore, every power of A is also a power of A inverse, and the converse argument will show that any power of the inverse is also a power of A itself. So that's why A and its inverse always generate the same cyclic subgroup. And therefore, by our second definition, if A is a generator, then A inverse is also a generator for our group. And for that reason, unless our group has order 2, generators are always going to come in pairs. And there's always going to be an even number of generators, because for every generator you give me, I can give you its inverse as another generator. And for that reason, phi of k is always an even number. The number of generators for a cyclic group is always even as long as my group has more than 2 elements in it, right? As long as we have an order that's bigger than 2.